You know how your phone can instantly find every single picture you have of your dog? Or how a self-driving car can navigate a chaotic city street? It honestly feels like magic. But it's not. It's a technology called computer vision. And today, we're going to pull back the curtain and show you exactly how machines are learning to see and make sense of our world. Okay, so to really wrap our heads around this, we have to start with the absolute core problem that computer vision is trying to solve. And it all comes down to this huge gap between what we call pixels and actual human perception. And this slide just nails the challenge. When you and I see a picture of a cat, our brain just gets it instantly, right? We see the shape, the fur, the context, the whole catness of it. A computer, on the other hand, it sees a massive spreadsheet of numbers. It has absolutely zero intuition. The entire goal here is to teach it how to bridge that enormous gap, to get from that raw data to something meaningful. And this number, wow, this just drives home the insane scale of the problem. For just one tiny image, a computer is staring at over 150,000 different numbers. Its job is to somehow find cat buried inside that giant sea of data. Think about that. Right, so at the most basic level, every single photo has to be translated into a language a computer can actually read. And that language is math. It's called a matrix. Each little pixel is broken down into 3 numbers, representing how much red, green, and blue light is in it. This grid of numbers, that's all the computer has to work with. That's its entire reality. So when you're faced with a data problem that big, you can probably guess that the old way of doing things, manually programming rules for everything, it just completely fell apart. It wasn't going to cut it. We needed a whole new approach, one that kicked off a complete revolution in how we teach machines to see. And you can really see that shift here. In the early days, you had brilliant engineers trying to hand code rules like a car has 4 circles for wheels or a cat has pointy triangles for ears. It was super fragile and just couldn't scale. But the modern approach, using deep learning, it's a total game changer. Instead of telling it the rules, we just show it thousands of cat photos and let the machine figure out the essential patterns of cat nests all by itself. And the undisputed hero of this whole revolution? It's a piece of tech called the convolutional neural network. You'll hear it called a CNN. This is the engine that drives pretty much all of modern computer vision. So this is where it gets really cool. How does a CNN actually do it? Let's pop the hood and take a look inside. The whole idea is kind of inspired by our own brains, which build up what we're seeing in layers, from simple shapes to complex objects. Yeah, that's the billion-dollar question, isn't it? How does it make that incredible leap? How do you possibly get from that giant spreadsheet of pixel values to a concrete idea, a useful label like dog? Well, the best way to think about it is like a digital assembly line for sight. In the first stage, you have these little filters that slide over the image, and their only job is to find the most basic patterns imaginable, like simple edges or curves or corners. Then, in the next steps, the network decides which of those patterns are actually important, and it kind of simplifies the information to focus on the good stuff. And this whole process just repeats over and over again, layer after layer, building more and more complexity at each stage. And what's so amazing is that as the data travels down this assembly line, it starts to build this incredible hierarchy of knowledge. The first few layers, they just see simple lines and blobs of color. A few layers deeper, they start combining those lines into textures and simple shapes. Go even deeper, and now it's assembling those shapes into actual parts of objects, like an eye or a nose or a wheel, until finally, the last layers can put it all together and recognize the complete object. Okay, so that's the how. Now let's talk about the where, because this technology is already woven into the fabric of our daily lives, often in ways you don't even notice. All right, first up, a classic, object detection. This is where the system doesn't just tell you what's in a picture, but also where it is. It literally draws a nice little box around every single object it recognizes and gives it a label. And I mean, this is absolutely crucial for self-driving cars, right? It's how they see pedestrians, other cars, and traffic lights. But it's also being used in security systems and even in retail stores to automatically track what's on the shelves. But what if you need more than just a box? Well, that's where image segmentation comes in, and it is a huge step up. Instead of just drawing a box around a tree, it identifies every single pixel that belongs to the tree, every pixel of the sky, every pixel of the road. It creates this incredibly detailed color-coded map of the entire scene. And that incredible precision is why this is such a game changer. This is what allows a medical AI to perfectly outline a tumor in an MRI scan for a surgeon. It's how your virtual background on a video call knows exactly where you end and your living room begins. But, and this is a really important but, for all this incredible power, computer vision is not magic. It's far from perfect. And honestly, understanding its weaknesses is every bit as important as appreciating its strengths. Because, let's face it, the real world is messy. It's not a clean data set. You have dramatic changes in light, from a bright sunny day to a dark rainy night. You have objects that are partially blocked from view. And then you have something really sneaky, adversarial attacks, where people can make tiny, almost invisible changes to an image specifically designed to fool the AI. A truly good system has to be able to handle all of it. Let me give you a perfect and kind of scary example of this. Researchers discovered that by placing just a few small, strategically placed stickers on a stop sign, they could fool a sophisticated self-driving car's AI into thinking it was a speed limit sign. And that gets to the absolute core of the problem. The AI never understood that a red octagon means you have to stop your car. It has no concept of traffic laws or safety. All it did was learn a statistical pattern of pixels that in its training data usually corresponded to the label stop sign. The moment those stickers broke the pattern, its recognition just fell apart. So, if you take away just one thing from all this, let it be this mental model right here. Computer vision, at its heart, is an incredibly sophisticated, hierarchical pattern matching machine. It builds everything from the ground up, from pixels to edges, to textures, to shapes, to objects, and finally to a decision. And that really leaves all of us with a pretty big question to wrestle with. We're building this technology into the most critical parts of our society, from our cars to our hospitals. So the challenge ahead is, how do we harness all of this incredible power while building in the safeguards to protect us from its failures, especially when we know it doesn't truly understand the world the way we do?